So now we have Javier Aizpurua, and he is at the University of the Basque Country. He's been at Chalmers University, at NIST, at Donostia, at San Sebastian, and he studies aspects of nanophotonics, metallic nano antennas, quantum plasmonics, many different aspects of nanophotonics. He's a new fellow of the American Physical Society, and he's going to tell us today about addressing quantum effects in nanocavity-enhanced molecular spectroscopy. So, Javier, please.
Thank you. Thank you. Can you hear me? Yeah. Thank you so much for the nice introduction, and thank you, Javier, for having me here. It's really a pleasure to address this audience, very young, as Roman said. I'm going to tell you about, I'm going to put myself here, about molecular spectroscopy in the context of nanocavities, right? And before I run out of time, I want to acknowledge the group, particularly Ruben Esteban, who is helping with a very talented group of students and postdocs. And our external collaborators, actually, Yuan Zhang in China, Thomas Newman now in the Czech Republic, and Mikolaj Schmidt in Sydney, who were former members of the group and now are having their own individual careers very successfully. And finally, the experiments. I will show many experiments today, combined with our theoretical descriptions of Shen Chaodong in Hefei, Jeremy Bamber in Cambridge, and Guillaume Schul in Strasbourg, okay? So this is what I plan to tell you in the next 30-35 minutes, a little bit about introduction of many things that you already know about cavities and how they enhance the spectroscopies, and I will focus on intramolecular resolution, and I really want to do molecular optomechanics today for this audience. Sometimes I skip this because of time, but today I really want to make it, I hope. So let's start with the very basics of molecules and molecular spectroscopy. We have basically two types of canonical excitations, vibrations and electronic excitations. We can excite vibrations directly with infrared absorption, and we can also excite vibrations via Raman scattering processes, inelastic processes. We can address electronic excitations via fluorescence, and the cross-sections of these processes in a few molecules or individual molecules are very, very small. So that's why, along the years, people have been using cavities to enhance this interaction of light and matter. You put here your molecules, your quantum dots, your bidimensional systems, and people have used the canonical Fabry-Perot and have tried to evolve into a variety of cavities and resonators to improve mainly two things, right? So we describe the effectiveness of the interaction via two parameters, the effective mode volume that we try to reduce, so it's some kind of the reduction of the electromagnetic density of energy into the volume of the matter we want to probe, and then the quality factor, the number of times the photons are bounced forth and back, so that you improve this many times the interaction with matter, right? So we try to improve this higher quality factor and reduce the effective mode volume, or the field enhancement, in other words, acting on the particle. And then through refractive and reflective optics, we have tried to reduce this and get into the plasmonic cavities that, thanks to the condensed matter excitation of the free electron gas, reduce the effective mode volume to sub-diffraction volumes. And the drawback is obviously that the quality factor, since the resonator is built on electron collective excitation, is very frictionful, and then obviously after 6-7 optical cycles, you lose the photons, the trapped photons or plasmonic photons, right? So for these photons trapped here, I'm going to talk about cavity photons or plasmon photons or nano antenna photons, and all will mean the same, okay, in this context. So that's what brought up the field of surface-enhanced spectroscopies, right? We can have this surface-enhanced fluorescence scattering, so you improve the fluorescence emission, the parcel effect, strong coupling. For vibrations, and I will focus today quite a lot on vibrations, you can have surface-enhanced also direct infrared absorption, but also surface-enhanced Raman scattering. And for all of them, this metal insulator, metal cavity will reduce, again, dramatically the effective mode volume. It will just localize the electromagnetic fields almost in the vicinity of a few molecules, or even single molecules, as I will show you in a second. How we address this? Let me show you an example of a canonical classical nanoresonator in the infrared regime. So we have a boron nitride ribbons. These are phononic nanoantennas, okay? And we can change the width of these ribbons. This is done with Rainer Hillenbrand in Nanogune experimentally. They increase the ribbon width, and then they redshift the resonances. So this is just a nanoantenna tuning. Instead of plasmonic, just phononic. And now we want to use this as an optical resonator, as a cavity, even if it's an open cavity, to enhance this interaction. We are going to put molecules, the vibrational fingerprint of a molecule that falls here at 1450 centimeters -1. And you can see how the interaction with the phononic resonator splits, produces strong coupling, and you can use your COMSOL simulation or even adopt a couple harmonic oscillator model to understand perfectly the splitting of modes, the Rabi splitting, and guess that you are in a strong coupling, right? So this is kind of a standard nowadays with your simulators and your classical models. What we have now and what we face in the last decade is the sophistication of these cavities, right? We have these two examples of sophisticated cavities, the STM, scanning probe microscopy. This is a molecule put here. It's a top-down approach, ultra-high vacuum, low temperature. It's a really sophisticated cavity. But we also have a more bottom-up cavities, right? A metal surface. We deposit here a self-assembly monolayer, another gold nanoparticle on top, and you sandwich the matter you want to probe, right? And this is done, for instance, in Cambridge and many other groups, right? But this is, again, a sophisticated cavity where you can probe very few amounts of matter, okay? How we address this, that goes beyond classical descriptions of COMSOL and couple harmonic oscillator models. We might get into a regime where quantum effects are important, and I'm going to tell you about the landscape that how we do in the group to focus and to address these issues, right? On the first approach, we adopt a condensed matter approach to describe the quantum effects of the electron gas that builds up the resonating cavity effect, right? So we solve a Schrödinger equation. It's a solution of this time-dependent Schrödinger equation, and this formalism allows us to address things that you cannot address in classical electrodynamics, like charge transfers, for instance, to mix transport and optical properties, right? There's another quantum aspect of these spectroscopies where you actually approximate the cavity through classical electrodynamics, but the matter you want to probe is described quantum mechanically via quantum chemistry, ab initio calculations, and you include these electron densities and current densities into your Maxwell-Solver equations, right? With this, we address also nanophotonics, picophotonics, electromagnetic complex, surface-enhanced spectroscopies. And finally, there's another quantum aspect which has not to do with the cavity or the matter you probe, but actually with the local fields you produce. And when you actually quantize the local fields associated to the cavity in a cavity QED fashion, you can address nonlinearities of the matter-cavity interaction, statistics of light emission, or address properties of non-classical states of light, right? Bunching, anti-bunching, etc. So this is a little bit the landscape of what we do in the group. And today, I'm not going to talk about this. I'm going to show you just one or two slides of what we do with this. It's just solving a Schrödinger equation in time dependent. As I say, this allows us to retrieve the induced electronic density in time. From that, you can derive the induced dipole moment, current density, electron transfer. This allows you to do a lot of things with charge transfer and really strong electronic coupling effects. This we do in collaboration with Andrei Borisov in Paris-Saclay. And actually, in the last, this goes too fast. In the last years, using this technique of condensed matter, we have addressed non-locality in plasmonic cavities, and I guess Asger Mortensen will talk about this in connection with Fableman parameters. This charge transfer and a strong field emission in these cavities, this we do with Alfred Leitenstoffer in constants, and you can retrieve the trajectories and the quivering of electrons in the cavities. It's very interesting, ultra-fast, strong emission. Response of nonlinear system from fresh principles. No need for hyperpolarizabilities or anything, and actual active control, right? So in this conference, actually, yesterday, Marina Quijada already used these techniques to address the combination of circularly polarized light and nonlinear response. So I hope you managed to see that, but you still have a chance to see tomorrow the talk by John Babase on quantum effects and non-locality with Fableman parameters and so on. What I'm going to talk today about is about the other two options, and I'm going to touch a little bit of this with an example of this, and another little bit of that with an example of that, okay? The first one I will do with resolution, taking these cavities to the stream to resolve Raman and fluorescence intramolecularly, okay? Again, let's remember what is a Raman process. We have a molecule or a piece of matter that can vibrate. The cavity assisted that, and it produces, Raman is produced when in an elastic process, an excitation to a virtual state, and a decay to an state which produces a phonon, in this case, a Stokes process, right? The use of these plasmonic cavities allowed to bring Raman signal to the single molecule level, okay? And this was done almost 25 years ago. I was actually a postdoc in Sweden with Michael Schell and Hongxin Xu when they started using these plasmonic nanocavities for the first time, 99, 2000, and check this, we call at that time hot spots, hot sites. Now we call them optical nanocavities, okay? It's the same thing. and that's where you put your hemoglobin, you see how the signal boosts, and it was done in a kind of synthetic chemist fashion, and Louis Lid-Marsan told us everything about it. He has been a leader in this field in the last years, and it's a very bottom-up approach, okay? The other option is to use this top-down approach that I mentioned in the beginning. This STM cavity is a fantastic, it's a paradise for a theoretician and for experimentalists. It allows you to identify a single molecule, put yourself there, and do really nasty things in electronics and optics to the molecule, right? In particular, you can localize a molecule, put yourself there, and then send light in, light out, and check, for instance, the Raman signal. I will go in a second to the fluorescence, okay? And 10 years ago, our collaborators in Hefei, Shen-Qiaodong, produced these wonderful Raman images of this single molecule. It's a porphyrin derivative, and you can put the STM tip, the cavity, on the lobe of the molecule or on the center, and you can get the Raman signal of a single molecule, identifying the STM. And if you put yourself in one of the vibrational fingerprints, you can actually scan the molecule, and get the Raman images of the single molecule. And this, as you see, has sub-nanometric resolution. And honestly, 10 years ago, at that time, I often say this, right? We didn't know why we were able to obtain this resolution. We had to ad hoc, so to say, assume a very localized sub-1 nanometer hotspot to reproduce in the simulation the kind of vibrational Raman fingerprints. So we did it, but we didn't know why. What was the source of this resolution in the cavity? Because if we remember what happens in a plasmonic cavity, in a standard plasmonic cavity, no matter it's an STM on a surface or two rods together, the kind of, with this radius of curvature of typical tips, the standard and 1 nanometer separation in the gap, the standard expansion, the standard extension of the plasma is about 5 to 10 nanometers in standard metals, right? And with this extension of 5 to 10 nanometers, it's very hard to explain how you resolve sub-1 nanometer resolution, right? So about 6-7 years ago, with Daniel Sanchez-Portal, we started digging a little bit more into the cavity, going to the atomic scale, and doing this kind of addressing of the cavity where you can see that the surfaces are not COMSOL perfect. They are atomistic, actually. And then we managed to do with Daniel in San Sebastian the calculation of the optical response of these kind of surfaces and particles that are not anymore smooth with the typical plasmonic dipolar here, but actually, on top of the dipolar plasmon, they show these atomistic features that localize photons in this few 1 or 2 atoms, okay? So this went too fast. This actually was done in cavities, in proper cavities, the full quantum calculation as a function of separation distance. We calculated this effective mode volume that I told you in the beginning controls the interaction of matter with this cavity. And we actually saw that the effective mode volume is below 1 cubic nanometer. And we termed this, with a little bit of abuse of the language, pico cavity. And don't get confused. The cavity is a pico cavity not because it's a cavity. It's a pico cavity because it's a pico resonator. Okay? So the pico cavity is just this part. And this pico cavity is mounted on a proper physical nanocavity. Okay, don't get confused by the language. A lot of people tell me, but where is the cavity in the pico cavity? There's no physical cavity. We use the term cavity to mean resonator. Okay, and we can see and address this even classically. I can see here a nano cavity in blue. You see the typical plasmonic enhancement, field enhancement as a function of the lateral extension, like 10 nanometers. I showed you that a couple of minutes ago. Now we start protruding this atomistic feature. This would be the pico cavity, and we can see how the field is localized below 1 nanometer. So this is the pico cavity mounted on the nano cavity. Okay? And with this field of the pico cavity, we can reduce these local fields, the effective mode volume, compare the nano cavity, lateral extension of the field to the pico cavity, and come with our molecule and do the calculation of the Raman. We do the calculation of the Raman in a sophisticated way. We have to actually multiply the derivatives of the polarizability expressed in atomic size and weighted by this inhomogeneous local field. You have this tool to calculate Raman in inhomogeneous, a strongly inhomogeneous field in this package or in this publication, and this allows us to actually use very strongly inhomogeneous fields of a pico cavity to map and scan any kind of molecule that you can address ab initio and obtain images of these molecules with these pico cavities, right? So after a few years, we finally understood why we managed to express this resolution of the experiment ad hoc at that time, and now with the action of a pico cavity localizing photons in a single atom and scanning. This is like a single atom with a photon attached there for a while, scanning the pico cavity. And this has been sophisticated, actually, 5 years later by Arab Karian. You can see that now the resolution, like in electron microscopy in STM also, and the optics has been improved dramatically, and they can map actually all the vibrational modes really, really nicely nowadays, okay? The same can be done for fluorescence, actually. But because it was first in Raman, I prefer to tell you like that. But in fluorescence, we can use the scanning probe microscope setup, the bias of it, to produce or to give energy to the system that makes the electron hole pair of the molecule to decay and get a photon out. And this we call electroluminescence instead of photoluminescence, right? The mechanism of electroluminescence is quite well understood at this point. We have the metal on the surface, metal insulator metal, a bias, electrons tunneling. Most of the electrons tunnel elastically, okay? But some of the electrons, a few percentage of the electrons, tunnel inelastically. Because of the bias produced between tip and sample, the electrons that tunnel inelastically are able to provide the energy in form of photons, and these photons are produced in a cavity. So the local density of photonic states tailor this emission, like in a parcel effect, and then this is really nice to explore. Let me show you, for instance, the plasmonic, without a molecule here, just the plasmonic emission of this electroluminescence, just the plasmonic cavity. This would be the cavity, the photonic cavity, okay? And this is the one we're going to use, putting a two-level system there, a molecule, HOMO, LUMO, and do stuff. In electronics, in STM, people have managed to map atomic orbitals, the HOMO, the LUMO, by differential conductance measurements, right? Without photons, you just put yourself on the molecule, you scan, and with this differential conductance, selecting the right bias, you can map the HOMO, LUMO. This is done with electronics. So now if we record the photons coming out in the same situation, the question is what kind of photon maps we can get, right, in this electroluminescence. This is the kind of things we get. I'm going to tell you in a second. So we can express this problem or address this problem in this cavity QED fashion, right? In a cavity QED problem of fluorescence, in a two-level system emission, we have this two-level emission emitting in a cavity, and the cavity is going to produce mainly, depending on the interaction, and the interaction, again, depends on the effective mode volume and the quality factor, is going to produce two effects, and you are mostly familiar with it probably. A broadening and an energy shift. And the broadening is what we call the parcel effect. You have local density of photonic states, and you kind of broadening the options to decay. And we also have the lamp shift. And they are given by the Green's function of this emitter, of this dipolar emitter in the cavity, which is the local density of photonic states. The imaginary part addresses the Purcell effect, the broadening, and the real part, the lamp shift. Okay? So in an STM, this STM tip on a surface with a molecular exciton here, we have exactly the same situation. If we want to address intensity, Purcell factor, and lamp shift of this situation, we will need to, or we might adopt frameworks of this cavity QED to address this situation. Let me show you an example of Guillaume Schul in Strasbourg. This is a free-base phthalocyanine. It has an exciton along this direction of the two hydrogens, and it shows a tautomer situation. So you have these hydrogens like this, or these hydrogens like that. They are equivalent. But because of how the molecule is deposited on the surface, they break the degeneracy. And if you measure the photoluminescence or electroluminescence of this molecule, you see two excitonic emission points, QX1 and QX2, which have to do with one tautomer and the other. And now you can put yourself in one of these energies and scan and get the photonic maps of electroluminescence of this free-base phthalocyanine. And again, you can resolve them because of the break of degeneracy of how they get on the surface. Otherwise, they would be completely degenerate, right? So the challenge is how to understand and reproduce that, right? And that's what we have to do. Now we have a tool, which is our pico cavity. We know that the effective mode volume can be picked up or in this single atom. And we also have the ab initio capability of addressing the electronic states of the molecule, right? So we have to combine the pico cavity description of the plasmon and the excitonic description of the molecule. And then we do that by the coupling strength. This coupling strength, which is basically the field acting of the dipole. But when the field is so inhomogeneous, like in the Raman, there is no anymore the possibility to address the dipole as a point dipole. You need to address the electronic density, the transition electronic density around the space, and also the space of the inhomogeneous field. We do that. We calculate the pico cavity. That you can use ab initio, but once you know it works with classical calculations, with no local corrections, you can address this kind of classical fields. You calculate with your best ab initio tool the molecular exciton, the electronic transition density. This is the dipole, it's positive, negative, but now it's not a point dipole anymore. It has its space distribution, and so does the pico cavity. We combine them, we convolute them, and we obtain G. And now with this G, we obtain G in each point of the space, following the scanning of the pico cavity, and that's what you get, a kind of dipolar map with subnanometric resolution. But remember that the experimental image looked something like this. So obviously we are missing something here. We have here the photonic part, so to say, of the intensity, but we are mixing features. So we need to realize that like in any other radiative emission process, the probability of emission has to do with this radiative chill, which is given by G, but also by the pumping probability. And in electroluminescence, this is not the local field to the square, like in photoluminescence. Here, there's a delicate balance of rate equation between states, and we found out that the pumping probability goes proportional to the density of the HOMO, of the highest occupied molecular orbital level, which looks like this. This is pure electronics, orbital. And when you multiply the pumping rate through the orbital, through the HOMO, by the photonic density of states, you obtain the final emission probability, which looks exactly like the experimentally obtained intensity map. So now you understand that this is a convolution of photonic information, dipolar photonic information, and electronic information of the orbital. Okay, it's very nice. The same, in one more minute about this, the same we can do not only with intensity, but also, as I said, with the Purcell effect and the lamp shift. But now, instead of using the Green's function of the point dipole for the imaginary and the real part, what we will need to do is exactly the same. Do the integral over the space of the electronic transition density and the plasmonic pico potential. And when we do that, and experimentally they can do that actually, they can move the tip up and down, control the tuning of the cavity, and then they can put themselves in one of the lobes or once they choose the lobe, they start scanning, and they can map both the peak width, the parcel factor, and the peak shift, the lamp shift. And as I say, we can do this integral, and with these tools, we can reproduce the lamp shift here and the parcel factor. This might be reviewed. This is, no, yeah, here, the lamp shift with the experimental peak and the parcel factor, which is the dipole with this one. So you can play actually these cavity QED games at the single molecule level with sub-nanometric resolution. In the last 5 to 10 minutes, I would like to touch this last part, right? Which is another quantum aspect of nanophotonics, which has nothing to do with the matter, but now our matter will be most usually a point dipole, and what we will do is to quantize the local fields, right? Let me show you this in Raman, actually. For that, I will remind you something that Romain was telling you about, which is optomechanics, right? And he started with something similar, maybe a more 3D sophisticated image. This is the same in 2D. It's a Fabry-Perot, right? It's a cavity, an optical cavity with a mode, a cavity mode of energy omega c. And one of the mirrors is attached to a spring, which has a vibrational mode, omega m, at the several kilohertz. It's a macroscopic mirror vibrating, so it's relatively slow for what I will show you in a second. So this system is a canonical optomechanical system because the radiation pressure of the cavity mode will exert on the mirror, will produce an activation of the vibrational motion. The vibrational motion will change and modulate the cavity mode. The change and modulation of the cavity mode will act again on the vibrational mode, and this is what we call a feedback action, optomechanical feedback action. And this is governed by a G, by an interaction rate of photons and phonons, right? So quantum mechanically, within a cavity QED framework, this is how we address it. And some of you will be familiar with it. We have the energy of the phonons, the energy of the cavity photons. It can be antenna photons, cavity photons, resonator photons. We have the coherent cavity pumping. We're going to pump with laser. And here's the interaction. Here's the optomechanical interaction in the simplest way, as people describe in optomechanics, which has basically the number of cavity photons and the displacement of the spring, right? This is the creation of a phonon, annihilation of a phonon. This is the space operator, right? And this is the optomechanical coupling, the single photon optomechanical coupling. What does this optomechanical coupling mean in standard optomechanics? Well, basically, it's the derivative of how much the energy of the cavity changes as a function of the motion of the coordinate of the phonon, okay? So the derivative of this energy cavity with respect to the displacement, this slope, is the coupling, the optomechanical coupling. More slope, more coupling, less slope, less coupling. If you do the derivation, and in the coupling here you can see pretty much the number of cavity photons. This is pretty much the square of the local field. This optomechanical coupling, very importantly, scales with inverse of the effective mode volume. Again, okay? Now, in the landscape of optomechanics, if now we plot this optomechanical coupling here with respect to the losses of the cavity, how fast we lose these photons, we can establish all this action, optomechanical action of different resonators, right? Colatoms, mirrors, microresonators. They typically have relatively low optomechanical couplings, but they behave very well, very good with losses. They have very strong, very high quality factors, right? So they are here in this landscape of the line that separates a strong and weak coupling. So this, until now, is the standard landscape of optomechanics and how optomechanics works. Romain has shown us nice examples of how you do with that, right? In macroscopic world with kilohertz vibration frequencies. Now we face the possibility to establish an analogy between the plasmonic cavity, which is just another resonator but in another regime of energies, and the vibrations of a molecule or matter that you put there, which is vibrations in a different regime, obviously much, much faster, okay? So we try to adapt all this cavity QED framework that describes optomechanics into this nanoplasmonics acting on molecule, and we call this molecular optomechanics, right? So how does it work? Remember that this was the optomechanical coupling Hamiltonian, right? With the G, this is the quantized field, is the number of photons, and this is the Stokes, the anti-Stokes, the creation and annihilation of phonons, right? And again, the G is this derivative. So you can actually use that in this kind of a standard Raman tensor and effective mode volume description, and you get to describe this optomechanical coupling as proportional to the Raman tensor, so more Raman tensor, more coupling, and inversely proportional to the effective mode volume. So you can play with the Raman tensor of whatever you put in your molecule and with your effective mode volume to increase this optomechanical coupling. So somehow, in this new regime of optomechanics, we are going very high in optomechanical coupling because the effective mode volume is very low, so this pushes us very high here, and one might think that it could put you here, but obviously the losses are also plasmonic, very strong, and it pushes you to the right of this graph, which puts you also at the edge of this optomechanical strong coupling line, okay? What can you do with optomechanics? Many, many things. It's a very intrinsic, non-linear process, if you wish, if you put in enough number of photons there. But as Roman said, you can red detune your laser with respect to the cavity and produce cooling, or blue detune, produce heating, so you can cool, you can heat. Actually, in Raman, sometimes people are interested in heating, actually, heating, blue detuning and heating to get more signal, right? And you can solve this rate equation, the master equation that I show you, and get to a rate equation of the population of phonons. And it has a pumping effect. It has also a decay, an optomechanical decay effect, and you get to an equilibrium and a steady population of phonons that involves the thermal population, but also some pumping through the cavity, and this is a pure optomechanical effect. So somehow we are changing the population of phonons, which is not thermal anymore, but through this optomechanical interaction, we can play giving and retrieving phonons on what the actual population of phonons is, right? How does it work? We're gonna solve these populations and this master equation for the plasmonic system on a molecule. So we're gonna calculate the emission spectrum. We choose plasmon energies, typical plasmonic energies, decay of plasmons, quality factor 10, phonon energies, around 100 millieV, the decay of phonons as well, and we adopt a coupling strength, which is given by the effective mode volume, basically, okay? And the Raman tensor of the molecule. And when we solve this as a function of pumping intensity, okay, we can plot the population of phonons and plasmons, and we can see how we can obtain a very nonlinear process of phonons. The population of phonons will give us the Stokes and the anti-Stokes spectroscopy. And let me identify basically the three regimes of molecular optomechanics. We have a thermal regime when the anti-Stokes signal follow a linear dependence with the intensity of the power of the laser. And then in the anti-Stokes, we start identifying a quadratic, a very nonlinear behavior, which is a result of this optomechanical interaction that in the Stokes happens a little bit later in what we call a strong nonlinear regime. So this will be the pumping regime, and this will be the strongly nonlinear regime. And this is what we got from our predictions, our calculations, with typical parameters of plasmonics and molecular strengths. And now, in this experiment done by Jeremy Baumber in this nanoparticle on a mirror that I just described, they use this biphenyl fortyl molecule here, and in cryogenic temperatures, basically they measure as a function of time the Raman spectra of these molecules. And at some point, they identify the emergence of certain non-permanent Raman lines, right? And what happens with this activation of non-permanent Raman lines is that in these cavities, even at cryogenic temperatures, some of the energy is deposited on the surface, popping up some atoms, creating these picocavities. There's no cavities, it's a picoresonator, again. And these picoresonators are responsible for the activation of these Raman modes. We did, again, this in homogeneous Raman calculations, locating the picocavity around the molecule, and we see correspondence of picocavity's location and Raman lines that they identify experimentally, okay? So actually the picocavity can happen here or here, but actually once it's produced, it just probes inhomogeneously the Raman line of this molecule from there and not from there, okay? So with that, we somehow push this optomechanical limit even a little bit more higher because the effective mode volume is even reduced to the picocavity, and then the G goes up. So actually, when these molecules with these Raman lines of the picocavity emerge, what the experimentalists did is to tune the intensity of the laser, and by tuning the intensity of the laser, they managed to identify experimentally that the Raman anti-Stokes line was going quadratically. And this is exactly what we found. So I just wanted to show you how this optomechanical description can address really interesting nonlinear effects and how we put optomechanics to a new limit or close to a new limit, right? And this is my last slide. In the last couple of years, 3 years, what we have done is to dig a little bit more into this molecular optomechanics. We have addressed some of the problems that have been mentioned here before. Resonances, collective effects. Ido Kaminer mentioned this. We are very interested in superradiance in this optomechanic context. We have addressed interesting effects here. We have also addressed the analog to the lamp shifting fluorescence in optomechanics is called the optical spring effect. And we have identified Raman, this shift of the Raman lines as you actually improve the cavity effective mode volume. And finally, for quantum information, with Alejandro González Tudela, who's here, 2-3 years ago, we started addressing the statistics properties of these two-color photon emission, right? Stokes and anti-Stokes, identifying areas of anti-bunching, bunching as very rich landscape to play with non-classical states of light. And with that, I think I'm done. I show you pretty much this. Optical cavities taken to the stream of picocavities, how they allow to do intramolecular resolution in fluorescence and Raman, and how they allow to take molecular optomechanics to the limit. The last slide of a little bit of advertisement, actually, which is for the kind of audience you are here. We are organizing the next Gordon Conference on Plasmonics and Nanophotonics in July in New Hampshire, together with Jason Ballantyne, and I really encourage you to attend if you can. And with this, I thank you for your attention.
Thank you very much. We have time for a couple of questions.
Thank you for the very nice talk. You talked about the emergence of these non-permanent Raman lines. If I understood it correctly, it's because of the emergence of new kind of picocavities. Mm-hmm. Normally, we understand Raman to be vibrational states with much longer lifetime than electronic states, let's say some kind of, four-wave mixing for SACARs, let's say. In this case, are these picocavities longer living than electronic states, or are they like virtual states?
No. This has, the existence of these picocavities has nothing to do with the lifetime of the phonon itself, which is still at the picosecond scale. If you manage to get a minutes-long phonon, that would be breakthrough, right? No, this is the minutes or the seconds existence of the picocavities, the activation of the actual atom, gold atom protruding for a while, and then merging again with the surface and disappearing and deactivating the Raman line. So it's not about the phonon lifetime, it's about the dynamics of the atomic migration and protrusion.
Okay. When you use the term non-permanent?
Non-permanent because of that, because it's attached to the picocavity lifetime. So if it's seconds, it lasts seconds and then they disappear and this Raman line disappears. But other permanent Raman lines are activated by the standard nanocavity. They are there. They don't need the extra effective mode volume reduction to be activated.
More questions?
There's like 3 or 4 here.
Yeah? Sorry. Yeah. Okay, very good. Thanks a lot. So this is done with STM. Is it also probing at the same time tunneling current? Can they do that?
Sorry? I had...
Is the microphone on? Yes. Okay. This is done with STM, the imaging you showed in the beginning. Do they also measure the tunneling current
Yes,
through
they
the
do.
molecule?
They do, absolutely.
Okay, but what you were plotting there was what was the...
What I was plotting there is a
measurement?
photon map
Was the photon map,
of
right?
a photon detector attached to the STM
Right.
cavity, while there is scan
Yeah.
with the tunneling current activating the plasmon and the exciton couple that
Yes.
emit light.
So my question is, what does the tunneling map look like? If yes, it's measured at the same time, so...
The tunneling map, depending on what you check, it varies also on this sub-nanometric scale, but that has to do with electronics.
Yeah, but the light also leads to photon-assisted tunneling, so there the light modifies
Sure,
the
but here
tunneling.
we are not in, I don't think we are in a regime of photo-assisted current, so to say. This is very well controlled, the molecule is physics-solved. There can be tunneling through the many body states of the molecule attached to the electrodes, and you do the electron transport calculation, but we don't activate here a photo current in that sense. Still, the cavity is like 1 nanometer separation, and the intensity is very low to avoid that, actually.
Okay, yeah, thanks.
Last question.
Yeah, my question is very general. Is how stable these molecules under this extremely high field. And my feeling is somehow the molecule probably distorted.
Yeah. No, this is actually contrary to what it might look from the plots with these colors. The field is not so strong. So the field enhancement in a picocavity in amplitude is like 3 or 4 times larger than on the nanocavity. Only 3 or 4, because it's like a lightning rod effect, and it pushes you 3. It's not like it boosts over 100 times, like the nanocavity. But this 3-4 times enhancement of the amplitude in Raman to the 4th power is 2 orders of magnitude.
My point is actually it's a static force, because if you
Use the microphone.
the tunneling regime, you need a very high electrical field. The field is actually extremely high.
No, but not so. We have done the calculations. I mean, we can talk later, but I can show you the numbers. It's not so. It's never more than 10 volts per nanometer. And the molecule is reproducible. You go out, you come back, the molecule is there. You don't destroy it. That's been checked.
Lunchtime. Thank you very much. Thanks to both
Thank
speakers.
you.